Deep learning research expanded so rapidly across vision, speech, and robotics that by 2018, the field required a unified taxonomy just to remain navigable. In March of that year, Alom and colleagues published a survey designed to consolidate this chaotic landscape into a single framework, indexing the specific design patterns that drove the first decade of the deep learning revolution. The timing of this document is significant. It captures the state-of-the-art just months before the release of BERT and the subsequent dominance of large language models. The survey organizes the field into three primary learning paradigms: supervised, unsupervised, and reinforcement learning. This taxonomy catalogs the methodologies used to scale 2D vision and sequence modeling before the industry-wide shift towards self-attention. To understand how we reached current AI capabilities, we must first isolate the 5 canonical architecture families and the historical benchmarks that established their mathematical signatures. Examining these specific constraints reveals the mechanical limits that necessitated the transition into the modern generative era. The foundation of the field is the dense neural network, or multi-layer perceptron. It operates through an affine transformation, where input values are multiplied by weights and adjusted by a bias. If you stack multiple linear layers without modification, the network fails. Because the composition of multiple linear functions is itself linear, a 100-layer stack mathematically reduces to a single linear map. To prevent this collapse, engineers insert a nonlinear activation function, like ReLU, between each layer. This function ensures that the output of each layer is not just a linear scaling of the input, allowing the network to approximate complex, high-dimensional data. Without these nonlinear constraints, depth is a mathematical impossibility. The architecture simply collapses into a single equation. Dense layers work for structured vectors, but they cannot scale to the millions of pixels in a high-resolution image. Convolutional neural networks, or CNNs, solve this by exploiting spatial locality. Instead of looking at the whole image, neurons focus on small pixel neighborhoods, using shared weights to achieve translation invariance. For years, computer vision error rates on the ImageNet benchmark remained high, but in 2012, the architecture transitioned from theory to dominant application. AlexNet won the 2012 competition with a 16.4% error rate. It proved that deep networks could be trained at scale by using GPU acceleration and dropout to prevent the model from simply memorizing the training set. This result initiated a 3-year architectural arms race focused on optimizing the depth and width of these convolutional stacks. By 2014, VGG16 lowered the error to 7.4% by using a uniform stack of very small 3x3 filters. This approach discovered that 2 small filters provide the same receptive field as 1 large filter with fewer parameters. Parallel to this, GoogLeNet reached 6.7% error by introducing inception modules, which process multi-scale convolutions simultaneously within a single layer. However, as networks reached 30 and 40 layers, training error began to increase. This was the degradation problem. The deeper the network, the harder it was for the optimization signal to reach early layers. In 2015, ResNet 152 bypassed this limit using residual skip connections. Instead of mapping the full input, layers only had to fit the residual error. This design reached a 3.57% error rate, which, for the first time, surpassed human-level performance on the ImageNet challenge. While CNNs process spatial grids, recurrent neural networks, or RNNs, handle temporal sequences by maintaining a hidden state that carries information from one time step to the next. Standard RNNs suffer from the vanishing gradient problem. As the error signal is multiplied backward through the sequence, it shrinks exponentially, eventually fading to 0. This means the network cannot learn long-term dependencies. It loses the context of the beginning of a sequence before it reaches the end. The long short-term memory network, or LSTM, solves this by introducing an explicit cell state, a dedicated information channel that runs through the entire sequence. Access to this channel is controlled by a series of multiplicative gating units. The forget gate discards irrelevant past data, the input gate admits new information, and the output gate regulates what the hidden state reveals. Because the cell state update is additive, it creates a highway where gradients can flow backward through time without being extinguished by repeated multiplication. In 2014, the gated recurrent unit, or GRU, simplified this to just 2 gates, achieving comparable results with fewer parameters and faster training times. These mechanical valves provided the first reliable method for processing long sequences, forming the basis for early neural machine translation. Supervised models rely on human-labeled targets. Unsupervised learning, however, focuses on discovering the underlying structure of raw data without external labels. The standard tool for this is the autoencoder. It uses an uncoder to compress input data into a low-dimensional bottleneck, and a decoder to reconstruct the original input from that compressed point. Because the bottleneck has limited capacity, the network is forced to ignore noise and retain the most salient features of the data. A limitation of this approach is that the latent space is discontinuous. You cannot simply pick a random point in the bottleneck to generate a realistic new image. Variational autoencoders, or VAEs, fix this by regularizing the latent space toward a standard Gaussian distribution. This ensures the space is continuous and interpolable. By forcing data through these severe mathematical choke points, networks learn to transform raw pixels into usable conceptual representations. Generative adversarial networks, or GANs, shifted the focus from data compression to high-fidelity generation by framing the problem as a game. A generator network tries to create synthetic data from noise, while a discriminator network tries to distinguish those fakes from real samples. This is a zero-sum minimax game. The generator only improves by producing data indistinguishable from the real distribution. Early in training, the discriminator easily wins, causing the learning signal to saturate. If the generator falls too far behind, the math produces near-zero gradients, stopping learning. To solve this, researchers changed the generator's objective from minimizing failure to maximizing the likelihood that the discriminator is fooled, ensuring a persistent training signal. Before transformers, this adversarial competition was the primary method for generating realistic synthetic imagery. Looking back at this 2018 survey reveals how the field was categorized just before the shift to foundation models. The original taxonomy includes deep reinforcement learning and transfer learning as standalone architecture families, but these are more accurately described as learning frameworks. Deep reinforcement learning doesn't use a unique architecture. It reuses CNNs and LSTMs as perception backbones to process state observations into actions. This survey documents the reach of deep learning in early 2018, a period where attention was largely viewed as an accessory to recurrent networks, used to help them focus on specific parts of a sequence. While the self-attention revolution would eventually replace recurrence, the underlying components remain. The residual connections from ResNet, the gating logic of LSTMs, and the optimization techniques documented in this era built the foundational infrastructure that current models still rely on.